Hi everyone. In this video, we are going to solve a crazy looking rational inequality where the different factors have a very high power. Like in this example, we have x minus 1 to the power 50 times x minus 3 to the power 51 divided by x minus 5 to the power 52 and also x minus 7 to the power 53. When an inequality looks like this, it looks kind of crazy, right? It's kind of intimidating. Like, oh my god, what are we going to do with all these, crazy looking powers and 4 factors and then numerator, denominator, what are we going to do? Well, no need to be scared. It is very easy to handle. The first thing we need to do is find the critical points and then plot them on the real number line. So let's do that. To find the critical points, what we need to do? We need to equate each factor with 0, and from there we find the value of x, and that value should be the critical point for that particular factor, right? So we have 4 factors here, 2 in the numerator and 2 in the denominator. So I have calculated the critical point for all 4 factors. Now let's plot them on the real number line. So we have plotted the critical points on the real number line, and the highest point is positive 7. So what we need to do? We need to draw the Wavy-Curve now, and to draw the Wavy-Curve, we want to start from the right hand side of the highest critical point. So in this particular example, our highest critical point is positive 7. So we are going to start from the right hand side of that point, and right hand side of the highest critical point will always give a positive value for the function which is on the left hand side of this inequality, whether you call it a function or the algebraic expression. The value of the expression will always be positive on the rightmost side or on the right hand side of the highest critical point. So there, what I'm going to do to draw the Wavy-Curve, we are going to start drawing a curve. Again, as I have explained in my previous video, that a Wavy-Curve is not a graph of the function. It is just an arbitrary graph that we are drawing to denote in which section or in which range on the number line that the value of the expression or the value of the function is positive and where it is negative. So it just indicates where the function value is positive and where it is negative. It's not a graph of the function. It is just an arbitrary graph that we are drawing to indicate where the function value is positive and where it is negative. If the graph is above the real number line, then in that range the function value is positive, and if the graph is below the real number line, then in that range the function value is negative. That's all we need to remember. It is not a graph of the function. It is just an arbitrary graph that we draw to indicate where the function value is positive and where it is negative. So what are we going to do? From the right hand side of 7, I'm going to start drawing the graph. So it will be like this. So let me start drawing it. I started above the line because right hand side of the highest critical point the function value will be positive, and the graph should be above the real number line to indicate that the function value is positive there, right? So this graph again goes all the way to infinity, right? Now, is the graph going to be above the real number line or below the real number line on the left hand side of 7? Well, that will be determined by the power of the factor that gave us this critical point. Now this critical point came from this factor. Let me underline it. It came from this factor right here, x minus 7 raised to the power 53. Now the power of that factor will dictate whether the graph should continue above the real number line or below the real number line. If the power is odd, which is the case for this particular factor, the power is 53, that is an odd number. So because the power is an odd power, the sign of the function will change. That means on the left hand side, as the graph continues to the left hand side, it should continue below the real number line to indicate that the function value is going to become negative now. So what I'm going to do? I'm going to continue this graph on the left hand side, but this time it will be below the line because the power of that factor that gave this critical point, the power is an odd number. I hope that makes sense. If the power is odd number, the sign of the function's value will change. If the power is an even number, the sign of the function's value would not change. And I guess that's a very common sense thing there, that no matter what value you have within the parenthesis, as long as you have an even power, it is going to become positive. That means it has no effect or no impact on the sign of the function's value. So for an odd power, the sign of the function's value would change. That means in this particular case, for critical point 7, as we go to the left hand side of 7, we need to indicate that the function's value now going to become become negative on the left hand side of 7 because that factor has an odd power, right? So let's continue the graph, and then we come to the point 5 and make a stop there. That is another critical point. Again, there we have to see what's going to happen to the function's sign of the value. So critical point 5 came from the factor which is this one right here. Let me underline. Critical point 5 came from this factor. I underlined with yellow, x minus 5 raised to the power 52. So one thing to notice here is that the power is an even number. 52, that's an even number. So no matter what happens or no matter what value we put for x for that factor, it will always come out to be positive because it has an even power. So in that case, what will happen? The sign of the function's value will not change. That means we need to continue the same trend that the function's value still continues to be negative. So we'll continue the wavy curve below the real number line. Even on the left hand side of 5, we will not go above the real number line because this particular factor has no effect on the sign of the function's value. That means whatever was the sign of the function's value on the right hand side of 5, the same trend will continue. I hope that making sense. Now we make a stop again at critical point 3 and let's see what happens there. So the critical point 3 came from the factor which is x minus 3. So it came from this factor, let me underline right here, which is in the numerator, x minus 3. Now what is the power? Well, this factor has a power of 51 and that's an odd number again. That means that factor will have an effect on the sign of the function's value. That means because it has an odd power, the sign of the function's value will change as soon as we go to the left hand side of the critical point 3. That means our wavy curve now should go above the real number line because we are talking about a critical point that has an odd power, right? So the sign of the function change. So now we are indicating that hey, on the left hand side of 3, the function's value becomes positive, right? Now we make a stop again at critical point 1 and let's see where it came from. Well, critical point 1 came from x minus 1. I underlined right here, that's in the numerator, and it has a power 50. It has an even power. So any factor having an even power has no effect on the sign of the function's value. So in this case, x minus 1 has an even power. That means on the left hand side of 1, the value of the function or the sign of the function's value will be same as whatever it was on the right hand side of 1. That means the sign of the function will not change at this critical point. Now before this critical point, what was the function sign? Well, it was positive. So the same trend will continue. That means if we continue our wavy curve, the curve will again continue above the real number line. I hope everything made sense up to this point. So all you need to remember is that when you are going to the left hand side of a critical point, just look at the power of that factor. If the power is even, the sign will not change, meaning you continue the same trend. Whether if you came from above the real number line, you continue to stay above the real number line, or if you came from below the real number line, you continue to stay below the real number line. That means the function's sign or the sign of the function's value will not change for a factor that has an even power. You need to be careful about the even power and the odd power. Whenever a factor has an odd power, that is where, or on those critical points, the wavy curve will change the direction. On other critical points, wherever the factor has an even power, the wavy curve will not change the direction. It will continue to be on the same trend, whether it's positive or negative. Whatever was the trend before, the same trend will continue. I hope it made sense up to this point. And now that we have our wavy curve drawn already, finding the solution set is very easy. So let's quickly indicate where the positive zone. Well, I'm using a red color here, so I'm putting a plus sign. So this is a positive zone which is beyond 7, meaning right hand side of 7, that's positive zone. And then between 5 and 7, that's a negative zone. Between 5 and 3, that is also a negative zone. And then between 1 and 3, that's a positive zone. And between negative infinity and 1, that is also a positive zone. Now in this case, what do you have to find out? Well, we have to find out that range of real numbers where the function's value will be greater than or equal to 0. That means the function value could be 0 or positive. So now we have to pick and choose those ranges of real numbers for which the value of this function will be either 0 or strictly positive, meaning greater than or equal to 0. Now what are the points where the function's value could become 0? Well, the function's value generally becomes 0 at the critical points, right? So if we highlight the critical points, now here is a critical point. Now I'm going to use a green color maybe. So let me use a green color here. So at critical point 1, the function's value obviously becomes 0. So I'm highlighting that with a green color here. And if you look at at it, if you look at the numerator, if you put x equals 1, meaning if you put 1 in place of x, then your entire function value becomes 0. So 1 is part of the solution. So I have drawn a solid circle here on this point that indicates the positive 1 on the real number line. So that means 1 must be included in our solution. Well, how about 3? Well, 3 also, yes, 3 also should be included in our solution because 3 also makes the function's value 0. So I'm doing a solid circle again on the critical point 3. And then let's look at critical point 5. Should that be included in our solution set? Well, if you use x equals 5, then your denominator will become 0 because x minus 5, that factor is actually in the denominator. So we cannot take 5 as part of our solution set. So 5 cannot be included. So I'm going to draw a hollow circle around 5. So 5 cannot be included in the solution set. And how about 7? Same story. 7 also cannot be included in the solution set because that would make the denominator 0. That's a dangerous thing, right? So 7 cannot be part of the solution set. So we are going to draw another hollow circle around point 7. So now you can clearly see that the positive zones are essentially between negative infinity up to 3, all the way to 3, because 1 is also included in the solution set. So from negative infinity all the way to 1, then again from 1 to 3, all of that is positive zone, right? Meaning in that range from negative infinity up to 3, the function's value is positive. And then if you look at it, between 3 and 5, function's value is negative. Again between 5 and 7, function's value is negative. But beyond 7, on the right hand side of 7, again function's value become positive. So we have actually two ranges that we need to include in our solution set. So how are you going to write the solution set? So our solution set will look like this. We can say x belongs to, one range would be from negative infinity up to 3. So let me denote that like this, negative infinity to 3. And is the point 3 included in the solution set? Yes, it is included. So we are going to use a bracket. Infinity always goes with parenthesis. And then also we have another range which is beyond 7, and that would be from 7 through positive infinity. Infinity always goes with parenthesis. And is 7 included in the solution set? No, it is not included. So we are going to use a parenthesis for 7 also, and we have to join them with a union symbol, and that is how we do the solution set. So this is our solution set for this particular example. Now from here, let's also do another solution set. What if this example was less than or equal to 0? Instead of having greater than or equal to 0 in the inequality, what if this inequality was given as less than or equal to 0? Then what would be our solution set? So let's try that. Well, if it was like this, if the condition was less than or equal to 0, meaning the function value must be less than or equal to 0, in that case we are going to use the same Wavy-Curve, because the Wavy-Curve would not change. It's still the same function, same Wavy-Curve, just the solution set will be different. Now we have to pick and choose the range of real numbers where the function's value would be 0 or negative, right? So now let's see where the function's value becoming 0 or negative. Well, you can see that function's value becomes 0 at 1 and 3, and also the function's value becomes negative between 3 and 5, and then 5 and 7. So we have two ranges plus one standing value 1, which is the number 1. So we have to include 1 in the solution set. So in this case we can say, okay, x should belong to, there would be one range between 3 and 5, and then 5 and 7. We have to break it because number 5 cannot be included in the solution set. That would make the denominator 0. So 5 must be excluded and 7 also must be excluded. However, 3 must be included and 1 must be included. So now we can write the solution set like this. Okay, just 1. So let's use the curly braces for 1. So point 1 is included in the solution set, and then we combine that with the next range, which is from 3 to 5. So we can say, okay, this will be from 3 to 5. Now is 3 included in the solution set? Yes, of course it is included. So we use the bracket. Now is 5 included in the solution set? The answer is no. So we are going to use the parenthesis. And then we have one more range. So we combine that with the next range, which is between 5 and 7. So then again, this will be 5, 7. Between 5 and 7. Now, are they included in the solution set? 5 and 7? No, they are not. So we are going to go with parenthesis. So this is how the solution set would look like if the inequality was given as less than or equal to 0, right? I hope it is clear up to this point. Now we are going to take a similar looking example. So let's again write down the example. We had x minus 1 to the power 50. Now I'm going to begin with, so this should be our example number 2. So let's take another example right here. So I'm going to write it as example 2. So for example 2, what we're going to do, we're going to take the similar looking inequality. It would be like this. Let's do like this, x minus 1, and I'm going to change the power. Let's make the power 51 right here. So this will be power 51, then times x minus 3, and we'll do a power 52, and then divided by x minus 5, let's say power 53, and then x minus 7 power 54, right? Let's see what happens here. So, and then we want to solve it for greater than or equal to 0 first. So we are going to solve it for positive 0 or positive, right? Non-negative. So now what would be the critical point? Well, the critical points are going to be same. So let me quickly draw the real number line here. Then the critical points should be 1, 3, 5 and 7. And if we plot them on the real number line, they're going to look like this. So we have plotted the critical points. Now we are going to draw the Wavy-Curve. So the Wavy-Curve will begin on the positive side beyond 7, right? On the right hand side of 7, it will be on the positive range. So we are going to draw it like this. We begin from the positive side and we make a stop at 7. Now we want to look at the critical point 7, meaning the factor that gave this critical point. We want to look at the power of that factor. Now in this case, you see the power is 54. The factor that gave us this critical point, its power is 54, which is an even number. Now because the power is even, it has no effect on the sign of the function. That means on the left hand side of 7 also, the function's sign will not change, meaning the sign of the function's value will not change. So we need to continue the same trend. So I'm going to continue the Wavy-Curve on the positive side itself. Then again I come to 5 and make a stop. Now at 5, should we change the direction? Well, 5 came from a critical point which is like this. This is x minus 5, which is in the denominator here. Now it has a power 53. It has an odd power. Because it has an odd power, it will have an effect on the sign of the function's value. It will change the sign of the function's value. That means on the left hand side of 5, as the Wavy-Curve continues on the left hand side of 5, the function's value actually becomes negative. That means we have to flip to the other side. So we continue below the real number line to indicate that, hey, in this range the function's value will be negative. And then let's see what happens at critical point 3. Well, critical point 3 came from a factor which is x minus 3, which is in the numerator, and it has an even power 52. That's an even power, and because it has an even power, it has no effect on the sign of the function's value. That means the same trend needs to continue. So on the left hand side of 3, we cannot go above the real number line. We came as a negative value and we need to continue the same trend. So I'm going to again continue below the real number line and come up to 1 and make a stop. Now what happens at 1? Well, on the left hand side of 1, actually the function's value will change because that factor has an odd power 51. The x minus 1 factor which is in the numerator, it has an odd power 51. That means the sign of the function's value will change. So far we have been on the negative. Now we need to go on to the positive side, which is above the real number line. So above the real number line is the positive zone. So that is how our Wavy-Curve going to look like. Now let's indicate that with a plus sign and minus sign. So this is a positive zone right here. That's a positive zone. This is a negative zone right here. This is a negative zone, and again this is a positive zone. And how about our critical points? Do we need to include the critical points in our solution set? In this case we have the equality sign greater than or equal to 0. So we have the equality sign, so we should try and include the critical points. However, we have to be careful about the denominator becoming 0. So if we take 1, no problem, the x minus 1 is in the numerator, so 1 should be included in our solution set. So I do a solid circle here, solid green circle on the critical point 1. And then how about 3? Well, x minus 3 is also in the numerator, so when x becomes 3, then also no problem, the function's value becomes 0. So 3 also should be included in our solution set. So I do a solid circle again, solid little green circle on the critical point 3. Now how about 5? Well, 5 cannot be included because it is a factor which is in the denominator. Even though we have the equality sign for this particular inequality, even though we have the equality, we still cannot include 5 because that will make the denominator 0, and that's a problem, right? So 5 cannot be included in the solution set. So I'm going to draw a hollow circle around 5. And how about 7? Same story. 7 also cannot be included in the solution set because it would make the denominator 0. So we need to exclude that. So I'm going to draw a hollow circle around 7. So now you can clearly see what would be our solution set. Well, we need to take all those real numbers which are giving a positive value for the function. So now let's scroll down here. So now let's write the solution set. So our solution would be x should belong to which ranges? Well, we have to take the positive ranges, right? So from negative infinity up to 1, and 1 is included in the solution set, so I use a bracket. And then we should also include the point 3, even though we don't include any other number between 1 and 3, or even between 1 and 5, because that entire range is negative range. However, there is one particular point which is 3, that is part of the solution set, because the function gets a valid value, which is a function becomes 0 at that point, which is a valid value for this inequality. So we have to include 3. So what are we going to do? Well, we are going to include 3 like this, and we are going to combine that. Then we are going to combine the other positive range that we have, and that is from 5 to 7. That will be one range from 5 to 7. So let's do like this. Neither 5 nor 7 are included in the solution set. And also we have another range which is from 7 to positive infinity, and 7 is not included in the solution set. Infinity always goes with parenthesis, and we need to combine that also in our solution set. So this is how our solution set would look like. That means you pick any value from these ranges or from this set for x, and your function will have a greater than or equal to 0 value, meaning the function will be 0 or positive. The function will never be negative for any value of x from this solution set. Now let's take the other condition. If we had the inequality as less than or equal to 0, then what would be the solution set? Well, let's try to write that down. So this solution set is for the condition when the function is greater than or equal to 0. So let me just quickly indicate that right here in yellow. I'm indicating that right here, that when it is greater than or equal to 0, for that our solution set would be like this, the way we have written it here, right? Now what if the function value or the inequality was less than or equal to 0? Well, let's see. So we are going to write down, if it is less than or equal to 0, then we are going to write the solution set again, right? So we are going to do the solution set when the inequality was given as less than or equal to 0. So what would be the solution set then? Well, this time we have to focus on the negative zones or the negative ranges wherever the function's value becomes negative. So here you can see the function's value is negative between 1 to 3 as well as between 3 to 5, and both 1 and 3 included. That means I can simply say, well, the function's value would be negative between 1 to 5, where 1 is included and 5 is excluded, right? So it would be a very simple solution. So in this case, your function's value becomes negative in the range between 1 and 5, and 1 is included in the solution set and 5 is not. So that's a very simple looking solution set right here. So yes, this will be the solution set if the inequality was given as less than or equal to 0. And in this range, you see 1 is included, 3 is also included, and those are the two critical points that we needed to include. So between 1 and 5, 1 is included because I'm using a bracket, and 3 is automatically included because it is between 1 and 5, and those are the two critical points we needed to include. And of course the negative range, which is between 1 and 5. So if we write the solution set like this, this will give us all that real number for which the function's value would be less than or equal to 0. I hope the concept of Wavy-Curve is clear now. I hope you now understand how to manage the different factors with crazy looking powers and stuff. So simple method, if the power is even, the Wavy-Curve will not change the direction. If the power is odd, the Wavy-Curve will change direction, and the Wavy-Curve always begins in the positive range on the right hand side of the highest critical point. If you can remember that much, then you should be able to draw the Wavy-Curve, and once the Wavy-Curve is drawn, then you need to carefully look at the critical points to see if the critical points should be included in the solution set or not, and of course the other ranges based on the condition on the inequality. I hope everything made sense so far. Thank you for watching. See you in the next video.